All right, hey honors chemistry. So I wanted to provide video notes for these next set of notes just in case you were absent or if you needed a refresher on what we talked about. So another set of properties that we know is the relationship between temperature and volume. We did this activity, or we did this demonstration and phenomena where I had a balloon and I put it on an Erlenmeyer flask with water, and I heated up the water, and the balloon, as the gas was getting into the balloon because it boiled and it had water vapor, as it went into the balloon, it got bigger. And I collected some data where I took temperature versus the volume of the balloon, and I got this graph. Now I could see that it's increasing, but there's an issue here, and we're going to call this the issue with degrees Celsius, right? So issue with degrees, so there's an issue with degrees Celsius here, okay? And so now, if I want to separate and look at this graph here, right, and I'm just looking over here, I notice that this graph does not go through 0. This is degrees Celsius versus volume. And it does not go through 0. 0. Does not go through the origin of 0, 0. And that's a problem because for matter, if I have 0 of one, I should have 0 of the other. So if I had a 0 temperature, right, and here's my 0 temperature, I should have a 0 volume. And so this is a problem or the issue with Celsius. I have to predict and figure out where my 0 volume would occur on this graph. And the way that I would do that is if I kind of go back and sketch back on this graph until I get to my x-axis, which would give me a volume of 0. So if I were to continue to go back all the way, all the way, all the way, I'd end up right here. And now this temperature, which has a 0 volume, is approximately negative 273 degrees Celsius. We're going to call this our new 0 temperature. And this is actually known as 0 Kelvin. We call this absolute 0. At this temperature, there should be no volume. And now, if I kind of make this a little bit bigger here, this is a graph of Kelvin versus volume. If you could see, I made like a smaller graph here, and it doesn't go through 0. And then when I zoomed in, now I have the bigger graph. I have a line that goes through 0, 0 here. My 0, 0 now is going to be 0 Kelvin. Okay? And so we need a new temperature scale. And so now a volume of 0 occurs at a temperature of negative 273 degrees Celsius. Jacques Charles determined that all gases had a 0 volume at this temperature. Right? If I have 0 temperature, I should have 0 volume. Should. If I have 0 temperature, I should have 0 volume. And we call this temperature absolute 0. Okay? And so from now on, whenever comparing pressure, volume, number of particles with temperature, we need to use Kelvin. Never use degrees Celsius in calculations. Don't do it. Not going to work. Okay, if I look back at the graph, degrees Celsius increases and decreases linearly, but it's not proportional. Degrees Celsius is not directly proportional. It's linear, but it's not directly proportional. If I double my temperature in degrees Celsius, I do not double my volume. Okay, but Kelvin is directly proportional to volume. So if I double my Kelvin temperature, I will double my volume. By the way, 2 times means double, just in case, or 2x means double. All right. Now, if I want to convert between degrees Celsius and Kelvin, I'm going to take my degrees Celsius, I add 273, and that's going to be equal to my Kelvin temperature. Now, if I wanted you to do a calculation with degrees Celsius, first you have to convert it to Kelvin, but let's say I wanted you to convert it back, to convert back. You're going to do the opposite. You take your Kelvin temperature, and you minus 273, and that's going to be equal to your degrees Celsius. Okay? And you need to know the difference between these two graphs. No. All right? Temperature versus degrees Celsius does not go through 0, 0, not through origin. And Kelvin versus volume does go through 0, 0. It goes through origin. You need to know how to read and interpret these two graphs, right? This is directly proportional. So if I had doubled my temperature, I will double my volume. Okay, so you're going to have to recognize these two graphs on your unit test for this unit. We're going to skip over to page 12 so we could do some more practice examples with increasing and decreasing factors. So it says a sample of gas occupies 120 milliliters at 25 degrees Celsius. What is its volume when the temperature is increased to 50 degrees Celsius and pressure and number of particles is constant? Okay, so let me put in this information. I have temperature and volume here. So my volume is 120 milliliters, and my temperature is 25 degrees Celsius, and I increase my temperature to 50 degrees Celsius. What is my new volume? Well, I increased my temperature, and the relationship between temperature and volume is directly proportional, so I should increase my volume. That means I need an increasing factor. And the only factor affecting my volume is temperature. That's the only thing affecting my volume. Okay? So I need an increase, and so the factor that I'm going to get my increasing factor from is from my temperature. But do not use degrees Celsius in calculations here. Not going to help you. So you need to convert this to Kelvin. If I want to convert this to Kelvin, I have to add 273. So 25 plus 273 is going to be 298 Kelvin. And then 50 plus 273 should give you 323 Kelvin. Okay, so now if I want to do this calculation with an increasing factor, that's a big over a small number factor, and I'm multiplying it times my volume. So I'm going to start with my volume, which is 120 milliliters, and I'm going to multiply by an increasing factor of my temperatures, but using Kelvin. If I want an increasing factor, I need to use big number over small number. So 323 Kelvin over 298 Kelvin. So I'm going to do 120 times 323. So remember, you do, like what we did dimensional analysis, you do 120 times 323 divided by 298. So times 323 divided by 298, and I get 130.067. 130.067 milliliters. If I wanted the correct number of sig figs, this has 2 sig figs. Both of these have 3 sig figs. My answer needs to be in the least number of sig figs. So between 2 and 3, I choose 2. And so if I want to convert 130.067 to 2 sig figs, I'm just going to say it's 130 milliliters. Remember that 0 is not, these zeros are not significant because there's no decimal point. So my answer with 2 sig figs would be 130. All right. Let's look at example number 4, another example where we just do temperature and volume. It says a sample of gas occupies 120 milliliters at 25 degrees Celsius. So again, my volume is 120 milliliters, And the temperature is 25 degrees Celsius. What is its temperature? So I'm looking for that. If its volume is decreased to 32 milliliters. Okay? All right, and it says number of particles and pressure is constant. All right, so if my volume here decreased, what must have happened to my temperature? Well, volume and temperature are directly proportional. They do the same thing. So that means that my temperature must decrease as well. So I need a decreasing factor. Okay? And again, the only factor affecting volume is temperature, and vice versa. So I need a decreasing factor with my volumes on my temperature. Can I use degrees Celsius for this calculation? No, do not use degrees Celsius in calculation. Do not do this. So what I need to do is I'm going to convert this to Kelvin again. So I add 273 and I get 298 Kelvin. And I don't know what my new temperature is. And I start by writing my temperature because I need to show a decrease in my temperature. I need a decreasing factor multiplied times my temperature to show a decrease in temperature. So if I want a decreasing factor, I need small over big multiplied by my temperature in Kelvin. And so small over big, I'll do 32 milliliters over 120 milliliters. And so I'll do 298 times 32. Remember, this is just like dimensional analysis with the type of calculation. 298 times 32, and then divided by 120. And I get 79.5 Kelvin. And if I wanted the correct number of sig figs, I would need 2. So I would say about 80 point. Or if you want, you could just say 79 Kelvin. Both of these will give you 2 significant figures. Look at the decimal point there. Okay? Now, if I had asked for degrees Celsius, X for degrees Celsius, I take this Kelvin and I subtract 273, and that's going to give me my degrees Celsius. So if I take 79.5 and minus 273, I get negative 193.5 degrees Celsius. If I still wanted to go on the 2 sig fig roll, now why 2 sig fig? This is 3 sig figs, this is 2 sig figs, this is 2 sig figs. That 0 is not significant because there's no decimal point, so my answer needs to be in 2 sig figs. It would be approximately negative 190 degrees Celsius. And is this showing a decrease in temperature? Yep, from 298 to 79.5, or 25 to negative 190. Yep, a decrease. All right, so we just went over and did more problems with increasing and decreasing factors. I have other videos in which we do problems with multiple increasing, decreasing factors, so you could use those. All right, if you have any other concerns or questions about how to compare different properties, we have other notes, but just remember that everything else is directly proportional except for pressure and volume. So this is on page 5 of the other notes. Pressure and volume are inversely proportional. So as V increases, P decreases. As V decreases, P increases. But everything else is directly proportional, just like our temperature and volume. Pressure and temperature will be directly proportional, and pressure and number of particles and temperature and volume and number of particles, they will all be directly proportional. If you have any other questions or concerns about the work we are doing here, please do not hesitate to reach out in the Remind.